What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
Summer concerts, pool parties, chill nights under the stars. We're stocking up our closet so you're ready to look your best for all of it. At Plato's Closet in West Ashley and North Charleston, we're buying all things summer. So bring in your tees, tote bags, sandals, sunglasses, and more. We pay cash on the spot for gently loved name brand looks. Plato's Closet is the go-to destination for trend-forward teens and young adults who support local and shop sustainable. Visit Plato's Closet today. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.
I'm Jonathan.
And I'm Gabriel.
And today we have on an episode that started out as a mini-sode, but it snowballed into a full episode.
Why are we mentioning all of this?
Because when we record mini-sodes, we still strive for quality. Because we're giving you something that is ours, and we like to be proud of that. But we also like to experiment with new equipment and new techniques. And that's when we do that.
That's right. And recently, we just got a new preamp, the thing that connects the mic to the computer. And we accidentally overdrove it, and you can hear that in this episode.
We're also telling you because this is an episode we're otherwise very proud of, and we decided it'd be better to let you hear it than not explain why it's like that.
That's right. The content is something that we are just so happy with, even if the audio sometimes gets a bit fuzzy.
So thank you for listening to Breaking Math, and we present Episode 18, Frequency. There is a new podcast that I would like to tell you about. It is called Physical Attraction. This is a very fun and clever show. The podcast aims to combine two separate topics, physics and clever pickup lines, into one. You heard that correctly. Learn about the universe and tips on chatting up a potential date. You can find the show on Apple Podcasts or wherever you listen to podcasts, and on Twitter @PhysicsPod. Check out the show. I think you love it. I'm Jonathan.
And I'm Gabriel.
And you're listening to the Frequency episode of Breaking Math. And today we have on
Tyler Jordan.
And Tyler, can you tell us a little bit about yourself?
I am an electrical engineer. I work in communications engineering, which is basically engineering the components and algorithms that let your cell phone talk to the network or let your computer talk over Wi-Fi to the internet, those kinds of things.
Now, you mentioned a few things that have to do a little bit with frequency, probably, right? In what capacity does your job have to do with frequency?
Almost everything. When you work in signal processing or communications, you think of signals or these waves in the air. You think of everything in terms of both time and frequency. So when did this occur? And then what frequency was it at? And you can think of those as musical notes kind of thing.
Awesome. Yeah, and before we start talking about frequency, we're going to talk a little bit about the origins of the study of frequency, which have to do a little bit with Aristotle. There's the famous story of Aristotle hearing a bunch of metal workers make beautiful sounds with their hammers by accident. And when he measured the metal, he figured out that they are whole ratios of one another. And that's one of the earliest music theories, and one of the earliest, even if it's not completely rigid, theories about frequency itself.
Yeah, and that is really interesting because, I'm saying, we think of these mathematical signals in terms of time and frequency, but our ears do that anyway. And whenever we listen to music, we hear not only that a note occurred at a certain time, but we also hear, was it low pitch or high pitch? And that actually corresponds exactly to frequency. As you were saying, the length or tension of a string or the metal that the workers are banging on. I'm Jonathan.
And I'm Gabriel.
And we're here once again to talk to you about Brilliant.org. Brilliant.org is where STEM happens. You can learn math, science, and more on their website. This time we're showcasing their CS classes.
If you've never done computer science, if you're just starting out, you can take their Computer Science Fundamentals course.
Or if you're more experienced, you could challenge yourself with a course like computer memory or neural networks.
These can help you in school or even professionally and in life.
So to support the show, and to maybe support themselves in life, where can they go?
They can go to www.brilliant.org/breakingmath.
And yeah, it'll help us out. And now, on to the rest of your episode.
Yeah, I gotta say, I'm actually really, really excited about this episode. I mean, frequencies are just about everything. There's a quote from Tesla, from Nikolai Tesla, that I didn't write down the specific quote, but he says something to the effect of his goal is to try to understand everything in the universe in terms of frequencies. So it's just a really cool avenue of mathematics. And also, as you had alluded to, we can talk about frequencies with, sound and music and ratios and anything that happens over time, as well as your current job, electrical engineering. So I think that this episode is really rich for things like analogies, and it's got a lot of applications. I think the goal for this episode, by the way, when we were planning this episode, we wanted to start off with just talking about conceptually what frequencies are. And then also at a very, very basic level, the kinds of engineering that people can do with frequencies. Things like AM radio and FM radio and how all that works.
Or even civil engineering design with buildings and bridges, and we'll get into that later, right?
Oh, yeah.
And an important concept when we talk about frequency is, of course, the sinusoidal wave. I'm going to give an example I came up with, and I think that you have an example that you wanted to give too. Mm-hmm. The one that I wanted to give was, if you've ever seen wheels on a train, there's always these two little segments that are connected by a straight line. So as the wheels go around, there's this bar that goes around in a circle. If you only look at the up and down motion of that bar, that's a sinusoidal wave.
Yes. So if you could imagine, like we were saying, with that kind of wheel analogy, if you see the circle and first you draw a horizontal line through that circle right through its center. And then we draw a line from its center to any point on that circle. Now that line is always the same length, and it's the radius. So as we rotate that line through that circle, we can always draw a triangle. One, the long side of the hypotenuse, and it goes out to the circle and then comes right down to that horizontal line. So this is a triangle. And so some people say a sine, cosine, how does trigonometry have to deal with waves? And so we're going to look at that point, that line as it rotates around the circle, and it always is drawing that triangle. And what the sine is the ratio of the opposite side from the angle to the hypotenuse. And since the hypotenuse is constant, we can look and we can say that is growing at a certain rate. It gets positive, and then it starts descending, and then it gets negative. And so, like he said, as that bar goes up on the rail wheels, we can see it goes up and down, up and down.
Real quickly, I'd like to say that one of these days, once our Patreon has enough, we'd love to have a live Breaking Math show where we all have little pads, little sketch pads, are able to show a lot of visuals, because I think that would be really helpful in this case.
And a visual, if you'd like one for this case, you could check out breakingmathpodcast.com/applets.html and click on the Fourier transform applet. It has a pretty good visual representation of not necessarily the triangle that was just mentioned, but of the lengths involved. Yeah.
And actually, I have one other analogy that I wanted to talk about with what a sine wave is, and I think it's really great that we're starting with these fundamentals. Sine waves are oftentimes, there's a term periodic motion. I think of a pendulum, or I think of, when we think of hypnosis, and somebody swings a pendulum of some sort back and forth, there's, one thing that's swinging back and forth. Well, if you imagine a pen or, something to mark on pencil at the end of that pendulum, and it went back and forth, if you move that pendulum forward, or if you move it in one direction as the pen is going back and forth, depending on the rate, you can actually have it draw out a sine wave, sort of.
And we call it a sine wave if you think, everyone's seen this when ripples in a pond. When I say a wave in water, don't think of a crashing wave or a surfer wave. Think of a ripple in a pond. And you see these little waves travel through the water. And so when we say a sine wave, we're essentially talking about that perfect ripple that's going through the water there. And so kind of think in terms of that.
Yeah, almost like an S turned on its side, and then it goes on and on. There, those are all my analogies for what a sine wave is. I'm assuming that that's quite adequate.
Oh yeah, for sure. Now, one thing that about sine waves, and we're going to get to other types of waves in a little bit when we talk about different types of transforms, but is that sine waves are just a very basic component, and they're used all the time in describing physical waves, EM waves, electromagnetic waves, and the Fourier transform. Now, the Fourier transform, we touched a little bit on it when I mentioned the applet earlier, but would you like to give an example of when you might want to use the Fourier transform?
So the Fourier transform is a really interesting piece of math, and what it does is it lets us take a signal or a function, something that happens in time. And so even my voice being recorded right now by this microphone, basically, a few thousand times a second, it measures the amplitude of my voice, and that goes through time. Now we can take that and we can send it through a Fourier transform, and the Fourier transform will take this time domain signal and put it into the frequency domain. It is a function that maps the time domain into the frequency domain.
Yeah, and that is quite a task for an audio podcast. So I'm trying to think of analogies, like how you have the same information, obviously in the case of the Fourier transform, it goes from something represented in time to something represented in frequency. But what's some kind of analogy for information, like maybe going from a spoken language to a sign language, I know that's not a perfect analogy, but I'm trying to convey the basic idea,
Well, one way of looking at it, I think, is you could think of when you go to the store, you could think of each moment that you're going to the store as a different thing. Like you're walking to the store and now you're picking up bread, putting it in the basket. Or you could think about all the frequencies involved. For example, you go to the store once a week. When you put the stuff in your basket, you're swinging your arms, and that has almost a sinusoidal thing. And that's not a perfect analogy either, but it shows kind of the basic philosophy in which a sinusoidal wave can be used to describe any periodic or bounded signal.
Yeah, and so what the Fourier transform essentially does, and this is kind of geared towards more mathematical folks who listen to this, but of course it can be understood by anybody who's listening to this, is that if you take a point in a room, you could say, okay, this is that point, it's on my couch, something like that. But what you could also do is you could say, well, let's project it along these three walls. And so you could say that is at this position X, Y, and Z in length, width, and height.
Yeah, and projecting along something just means if the walls were made out of mirror and you looked right at the mirror, you would see yourself and the point where it projects it. So it's like you're the direct shadow, or so you're projected onto the globe during high noon, for example.
Yeah, it's like a shadow of the point on each wall, and how high it is on the wall, how far in from the corner it is, and how far in from the other corner on the floor. And so you can think, okay, I took this point, and instead of just thinking that's on my couch, now I can say it's at X, Y, Z coordinates 4, 5, and 6. And so what that gives us is, okay, what if it was at 4, 5, 17? We know the dimension in the Z direction, is 17 inches off the ground. And so that tells us something more than here's this point in the room. We can actually start looking in these different directions. And much the same way, a Fourier transform of a signal, maybe you look at like the ripple in a pond. And if there are two frequencies going on there, it's easy to see with one, but with two, you see a ripple on a ripple. It's like it's a ripple on a ripple, and you can hardly see what's going on. It starts to look garbled, but when you take the Fourier transform of it, it becomes very clear. You see one frequency, you see one tone at one frequency and one tone at another.
Yeah, actually, that's a really great topic. When you talk about one signal riding on top of another signal, I think that really is almost the crux of a lot of signal processing, right?
Yes, and so what we're saying, if we put it back into this vectorized, thing that I was talking about, and the point in the room is you could say, oh, this is 3 inches along that wall, 5 inches along the other wall, and 17 inches up. The same thing, we could say, hey, this frequency is 2 parts of a low frequency wave and 5 parts of a high frequency wave. It's basically decomposing that signal into its frequencies. So something that I wanted to bring up is that we see this with radio stations, okay? If you could see the electromagnetic waves in the air from radio stations, it would be garbled and confusing. You wouldn't be able to see anything. But if you take the Fourier transform of that, then you can see it in terms of frequency, and you see these very neat stations. They're all aligned, so you would see along, and we'll talk graphically mathematically, along the x-axis, instead of time, how the signal changes in time. You don't know what happens in terms of time now. Your x-axis is now in frequency. And so what's nice is you could say, oh, look, at 102.5 megahertz, there's a station, and then there's a little gap between that and 102.9, which is, the hard rock station. And you can see, hey, if I just take everything that isn't my 102.5 and I filter that out, then I'm only left with that station. And so you can look at things, and this is where it gets into electrical engineering and signal processing, is you can filter everything unwanted out by frequency. Okay. And then in the time domain, you play it through your speakers and you hear wonderful classic rock. Oh,
that's totally cool. Yeah. So now, when you brought up the whole idea of the frequency, like on an old radio, and you turn the dial back and forth, that's actually really, really effective, I think. That's cool. So I'm wondering, is it a good time to segue into another topic involving frequencies, and that is wave modulation? In other words, how is it that in electrical engineering, how do we encode information onto waves?
Yes, this is actually my favorite thing to talk about, because this is my bread and butter. This is what I work with.
Oh, that's so cool. That's so cool. I'm gonna let you take the wheel on this one.
Well, before we do that, is there any way you could just define what modulation is for us?
Yes, exactly. And so you can say modulation is basically how we want to change a physical phenomenon to transmit information.
Okay, very good.
So you ever do that thing where you get the 2 cups and you connect them by a string and you can talk over it? What's actually happening is your sound waves from your voice are modulating on that string. And so sound waves aren't traveling between your cup and your friend's cup. They're actually traveling on that string. And that string is then vibrating your friend's cup, and then you can hear it. So that's a form of analog modulation.
Awesome. And so everybody knows 2 different types of modulation, just right off the bat, even if they don't know it. AM and FM. So let's go into those.
Yes, AM, FM. So those stand for AM, that's amplitude modulation, and FM is frequency modulation. So I have a guitar here. I'll kind of display that for you. Amplitude modulation is saying, okay, if I want to send you one signal, we'll take digital modulation. I want to send it 1 or 0, or, I want to send you 2 different values. I'm going to modulate the amplitude of that signal rather than the frequency. So it would sound like this: a quieter tone and then a louder tone. And so using those different volumes, we can transmit information. And that's one very frequent way to transmit information. Another is to use different frequencies. So if I want to say one thing, I will transmit this tone. In another, I'll transmit the higher tone. And there's all sorts of different tones, and this is all different frequencies. And so there are a bunch of ways we can do this. And so if you think we're gonna go back to what a frequency actually is a cyclical motion. It's you riding your bicycle and your foot going up and down however many times a second it does. And so amplitude in this case would correspond to how large of a circle your feet trace when you pedal your bike.
Yeah, so like if you were a little kid with a very small bike, that would correlate to a higher frequency.
Not quite a higher frequency, but a lower amplitude.
I'm sorry.
In kind of my
correction. Yes.
Well, it would be a higher frequency if the wheels were smaller, but that's a different topic.
Yeah, we're just going to look at the crankshaft here because, there's all sorts of gear ratios, and But so that would correspond to a larger amplitude is a larger circle that your feet trace.
Yeah. Ooh, I guess I would be right if we were to say, if a bunch of different sized bikes were to go the same distance at the same time, one of them would have to be a higher frequency because you're spinning around. There's more circles involved.
Yes, that is true. And then you could say, okay, the frequency. If we're doing the circular motion, the frequency is how many times per second your feet are cranking that bike. And so are you cranking it 1 time a second or 2 times per second? That's the frequency. It's just how fast you're going, really.
Now, as far as I understand it, there's benefits and detriments to using AM and FM. Mm-hmm. And why are those? And what are those?
Some of them have to do with the actual frequency these are transmitted at. AM frequencies tend to go further. That's because they're a lower frequency, and FM don't go as far. Now, when FM came out, it had a much higher fidelity because the noise that is always occurring in the amplifiers or in the air, it doesn't affect angular modulation, such as frequency modulation, as much as it does amplitude modulation. And so it was found that you could get a much higher fidelity recording pass through the air with frequency modulation rather than amplitude modulation, because instead of just looking at what we call the envelope of the signal, which is the loudness of it, the frequency modulation always assumes it's the same loudness. It's only looking at the frequency at which it's transmitted at. So if you do have some noise, it may make your signal sound quieter, but we're not looking at the volume of it. We're actually looking at what frequency we're transmitting. And so that's kind of a simple explanation why FM is better modulation, at least for audio transmission.
So with respects to AM and FM, there's also a lot of considerations with how they interact with things like clouds. And why is it that AM goes much further than FM? Isn't it based on the size? Is this... I want to make sure I'm not making
the wavelength.
Yeah, that's correct. Yeah. Thank you. Based on the wavelength, of course. I believe that AM, it goes right through them, but FM bounces off them, I think.
Yeah, so you'll notice if you go on your FM radio, you'll have these stations like 770 or 1080. I don't know the last time I tuned into a AM radio station, and those are in kilohertz. Those are in thousands of hertz per second. So that's 770,000 times a second this wave is going up and down. And since it's going, it has a certain wavelength associated with it, a longer wavelength. That is, as ripples in a pond, you could measure the distance between 2 peaks in that ripple, and that would be your wavelength. Now, let's say you're splashing your finger in the pond quicker. That frequency, as that frequency goes up, the quicker you do that wavelength shortens, and these are all related with the speed of the wave. But anyhow, the wavelength does change, and so with FM radio, they also transmit at higher frequencies. You get 102.5 or 94.1. I'm giving away my musical tastes here if you live in Albuquerque, but what that is in megahertz. That's almost 1,000 times more frequent that this wave is cycling, and so that wavelength goes down by almost 1,000. It's more like 500 or 200, and so as that wavelength shortens, it actually interacts with physical objects differently. It'll travel through the atmosphere differently.
Interesting. One thing that you brought up, and I wanted to make sure that's cemented in the minds of the listeners, is that frequencies are related to wavelength. And that's only because frequency doesn't change the speed in which it propagates, right?
Correct. Things, for the most part, but yes.
Unless you get into advanced stuff, probably.
Yes, there are certain materials but we won't get into that.
All right, wonderful. So, yeah, let's talk a little bit more about the Fourier transform. So what was the initial motivation for the Fourier transform? As far as I understand it, it was solving the heat equation on a ring. Now, the heat equation, backing up a little bit, is a differential equation, which is just an equation that describes rates of change and how they relate to one another, that describes how heat is transferred. And if you have what's called a periodic boundary condition, which you have on a ring, it gets a little bit more complicated, and he had to invent this whole type of math for it. Do you have anything to add?
Not much to that because I'm not a mechanical engineer or heat transfer expert at all, but it is interesting that something that was invented for one purpose, heat transfer, somebody could apply it to something like audio engineering or electrical engineering, communication systems, signal processing.
And I would also like to talk a little bit about the uncertainty principle inherent in the Fourier transform. Do you have anything to say about that?
Oh, yes. What's interesting with the Fourier transform, at least when it's implemented practically, the Fourier transform, it actually takes an infinitely long signal, okay? And then it transforms it into frequency. Now, in real life, we can't record an infinitely long signal. So when we take a Fourier transform, we only take it over a certain amount of time. Now, what's interesting about that is the longer time we take that Fourier transform over, the more information we know about frequency, the higher resolution in frequency we have. And so that's really cool because you can say, oh, that tone, it's at exactly 440.0015 hertz or something, if you're getting into audio engineering kind of thing. Now, the problem that gives now is that we know exactly the frequency, but we have no idea within that window when that signal or that tone appeared. And so the more we know about frequency, the less we know about when the signal occurred. And similarly, if you take that when you say, oh, okay, I want to know exactly when that signal occurred, you shorten your window, okay, and then you take this transform, you say, hey, I know where it occurred much more accurately now. Now that you know that, because your transform is over such a smaller window, you don't have the frequency resolution. You'd say, oh, it's at 410 hertz or 430 hertz, but I'm not sure in there. And so it's interesting, the more you know about one aspect of this occurrence, the less you know about the other.
Interesting. And one place where this comes up every day, well, not necessarily directly or not in a way that we could actually even see with our big eyes every single day, is the Heisenberg uncertainty principle. If you take position and momentum and make them, one of them the frequency domain and one of them the space domain, you get the Heisenberg uncertainty principle, which states that the more you know about the momentum of a particle, the less you know about the position and vice versa.
I just want to say how happy I am that we're talking about the Heisenberg principle on Breaking Math. But I did want to, that's a very interesting application there. But yes, the more we know of a particle's position, the less we know about where it's going. And we can see that exactly in what we're talking about with the time and frequency uncertainty.
Now, one topic that we brought up during the planning of this episode was resonance. And an example I wanted to bring up about resonance, actually, you came up with this one. Why don't you talk about the swing example?
Oh, yes. So there's something engineers we take into consideration when we make designs, and that's the resonance of something that deals with a reoccurring force. So we can think about this as a swing set. Okay, so somebody's on a swing set, and this is essentially a human pendulum, and we've seen people get very high on swing sets, but they never got that high with one push. And you'd have to be pretty strong to do that, and you'd have to put a lot of force, wouldn't be very comfortable. But what we do is we push them a little bit, and then they swing back, and we push them again. They get a little higher. Swing back, push them again. They get a little higher. And what this is doing is we're applying a periodic force to the person in the swing set. This is a frequency. This is frequency math. If we were to take this, you're saying, I'm just pushing every 1 to 2 seconds. Now, we could take the Fourier transform of that and say, so that's about 0.8 to 1 hertz. And so I just give that as an example that, hey, we can take anything and look at it in the frequency domain. But you could have never put that much energy into that person in one push, but over 7 or 8 pushes, you can get them at the top of that swing set, and they have a lot of energy going there.
Now, how is that different from using something like a jack on a car, where you do the same motion over and over again, and you get an accumulated effect?
Yeah, so the jack on the car, that is kind of an interesting example. It's not dynamic, it's static, and so it has a little latch on it. First of all, you use a lever, which multiplies your torque or your force, and you just go up a little bit at a time. And so you are still applying the same amount of force needed, but you're just latching it up a little bit at a time. And that it is kind of a similar example, but we have to do this dynamically and at the right time apply the force.
So it'd be true resonance if the car bounced up and down.
Yes. We see these guys on Central Saturday nights do that. It's really interesting.
And of course, there's the famous, we'd probably be amiss if we didn't talk about it, the possibly apocryphal example of Nikola Tesla vibrating his building in New York. He had a machine. It was a very, very well designed machine. It took into account the difference between air pressure densities and things like that to create mechanical vibrations. And he was trying to tune it to the vibration of his building, and apparently he heard a cracking sound or something.
Yeah, so this is kind of it's a myth, kind of. I don't know. Mythbusters did a little episode on it, and basically what it is a little machine, and it had a little oscillating weight in it. And it worked the same way as a swing set. Imagine somebody very small, like an ant pushing on a swing set. Theoretically, if there's not so much damping, that is friction, they could just keep pushing just a little bit at the right time, and that energy would accumulate. And so that's what he was trying to do with this, a little weight just moving back and forth, and it would find the natural frequency of a building. And so when we strike a piece of metal, like, what did you say, Archimedes?
Oh yeah, I think it was Archimedes.
Archimedes or a guitar string, it vibrates at its particular resonant frequency. And so what this thing was trying to do was trying to find that resonance and push it just at the right times.
And does resonance have anything to do with the Dirac delta function? The Dirac delta function, for those unacquainted, being like you clap in a room and you hear the echoes of the clap, so you know what the shape of the room is.
Yeah, a little bit, yes. That would actually give us the impulse response of that room, and we talk about that in terms of filtering, that the Dirac delta is, it's essentially a clap, and that clap is this impulse, and that impulse contains all frequencies possible, but in theoretically zero amount of time, or infinitely small amount of time, rather.
And of course, if you clap in the frequency domain, you get a pure tone in the time domain.
Yes. So if you take, like we said, like that clap is just an impulse. It gets really loud, really quick, and quiets right back down. And so when we take that into the Fourier transform of that, it's a straight line through all frequency. It contains all frequency. Now, what this does is, you're saying, look at the shape of the room. It's letting that sound go out to the shape of the room. The tones that don't resonate just get quieted down. The tones that do, they linger a little bit, and then they come back to your microphone. And your microphone picks up only those tones that linger. And so the room is actually acting like a filter, kind of like we were saying with the radio stations. You're putting out all frequencies all at once in this clap, and then you're listening back for the frequencies that remain and aren't damped.
Wonderful.
There is an example with the Tacoma Narrows Bridge, which is a bridge up in the Northwest that they had built this over this canyon or gorge, and during a windstorm one day, the bridge had been shaking, and during one day they went out and filmed it when it was going out of control, and just this wind blowing over this bridge, these aerodynamic forces, it found the resonant frequency of this bridge. And you can look this up online. Please do. If you're listening to this podcast, the Tacoma Narrows Bridge, it's an amazing piece of footage. And this bridge is swinging like a rope. It has cars on it. People are trying to run off this bridge, and it's swinging back and forth because that wind has excited that bridge at its resonant frequency. And when it resonated there, it got out of control, and the bridge just tears apart and absolutely destroys itself.
Yeah, definitely. With resonance, you can get all kinds of bizarre effects. The one that I think a lot of people are familiar with too, and this might be one of the last examples we give, is the opera singer who sings and then breaks glass. Apparently, they are not able to replicate that on MythBusters, I think, but I might be wrong.
Actually, I have heard of one other example. There was an earthquake in Mexico, and certain buildings that had a concrete that was the same resonant frequency as the earthquake. There was some tragic collapsing of buildings, and I think that learning from that, buildings are no longer made the same way. In fact, there's a whole field into how to construct buildings that are earthquake-proof, in fact.
Yes, there are. So with the Tacoma Narrows Bridge, it's just a perfect example of, hey, civil engineers, let's definitely do some frequency analysis on this, so that on all the civil engineering, all these buildings, so that we don't hit a resonant frequency. And so the way they avoid this is essentially using filters. Part of the building is made out of something with a certain resonant frequency, but they know that. But it does not resonate at other frequencies. Then they use another part of the building is made out of material that will resonate at another frequency, but not at the first material's frequency. And so they actually filter out each other's frequencies, which is really interesting. The other thing that they do is, you could look this up too, it's incredible. They have these giant weights that are in these skyscrapers in San Francisco. So when the building shakes, this weight kind of stays in the same place, and it acts as a damping force. It acts as something it can anchor itself to rather than the earth.
Wow.
The math that is used to analyze these resonant frequencies, it's very similar to the Fourier transform, and it's called a Laplace transform. It's actually a generalization of the Fourier transform.
And before we talk about that, let's do a quick refresher on the complex plane. The complex plane is like the complex number line, but instead of having one dimension, you have two dimensions. So where one dimension, you have things multiplied by the square root of -1. If you'd like to know more about that, you could check out our episode, Wreaking Chaos. It's episode 2.
But we should do there is an imaginary episode of Breaking Math about imaginary numbers. Perhaps it'll become real.
Only if we multiply it by its complex conjugate.
It's going to be quite a complex episode. You'll have to follow along. So if the Fourier transform is taking a signal and mapping it into frequencies, the Laplace transform takes a signal or a measurement through time and maps it into the complex and real exponentials. And now this is like kind of mind-blowing if you're listening, because you go, wow, like complex exponentials, but we'll get into that. If you think of an exponential, that's something that either increases at an increasing rate or decreases at a decreasing rate if it's negative. And so what the Laplace transform lets you do is it lets you take a response of a material or building and our control system or a filter, and it lets you look at it in terms of these exponentials. Now, a complex exponential, let me just say this, it's going to take some proving to do, but a complex exponential is a sine wave. It's a periodic wave, and it never decays. So when we look at the Laplace response of something such as how a building moves during an earthquake, or how a control system moves an arm or something, or a robot, we can see if we map this to these exponentials, if anything maps to a positive exponential, we can say, oh, that response, that is the shaking, the vibration, whatever, it will increase at an increasing rate. That is not good. That is resonance. And that is what makes the Tacoma Narrow Bridge blow up.
Interesting. And you said that during the planning, there's a transform related to the Laplace transform, but for discrete time signals. Do you want to talk at all about that?
Yes, and so maybe we'll have some reference sheet on this that you can look at later, but it's essentially the same thing, but instead of applying to exponentials, that is e to the something times something, we actually just map it to a complex number z, and that can be anywhere in the plane. And what that does is, if the purely imaginary axis of the Laplace transform, okay, we're in the plane, just the imaginary axis, which conventionally is the vertical axis, That is the Fourier transform. Okay, that is a purely imaginary exponential, which is a frequency. So you could take the Laplace transform and only look along that axis, get the Fourier transform. With the Z transform, it actually maps the Fourier transform onto the complex plane, but actually in a circle. It's the unit circle about the origin. This is important because when we get into discrete signals, we talk about sampling, and that sampling is actually cyclic. And so if we follow along that Fourier transform, which is that unit circle, eventually we'll end up back where we started. And that's something that brings up, I think, our next topic, which is sampling, Nyquist sampling.
Indeed, yeah. Nyquist sampling is fascinating. We did a lot of planning, and our guest did a lot of planning for this episode. You had a great example of aliasing. And aliasing, for those who are unacquainted, is like... actually, why don't you take it away?
So when we get into sampling, what we're saying is, okay, if we want to record something, let's say you're doing a scientific measurement, you want to record temperature every second. And so you open your eyes, you look at the gauge, and then you write down the temperature, and you do that every second. Okay, you could do the same thing in terms of any measurement you take. And so this is really important when you're doing these scientific studies and you want to measure these things. However, there's some things you got to be careful of. When we're looking at these frequencies, there's some assumptions that, if you make that could be fatal to your experiment, to your analysis. So let's take the crankshaft of the bicycle into account again. Okay, we're going to look at the bike from the left side of the bike, if you're standing on the bike, and someone's riding forward. Maybe it's a stationary bike. That's easier. And they're going to start with their left foot, and it's going to be on the back at 90 degrees. And we'll call that 0 degrees, actually. It's going to be, the left pedal will be near the back, the right pedal near the front. Okay. Now let's say somebody starts riding forward, and you're going to look up once a second, and you're going to record the position of that person's foot. And then you can say, okay, well, I know the position, and I know the time. Now I can take the frequency analysis and know the frequency of how fast this guy is pedaling. Now, that works up to a point. So if you take a measurement every second, and this person is turning the crankshaft a third of a rotation every second, you're going to open your eyes and see they're at that starting point. Then you're going to look down, write your number down, you're going to look up, and you open your eyes, and they're a third of the way around the crank. You write that down. The next time, they're 2/3. The next time, they're back where they started. So now you go, okay, so this is good. I know that they're going at 1/3 hertz. Every second, that crank travels 1/3 of the way around the circle. And you'd be right in this case. However, you start running into problems when that frequency gets faster than half your sampling rate. And let me explain this. Let's say instead of a third of a rotation per second, they did an entire rotation per second. Now every time you look up and you open your eyes, okay, they're where they started, you look down, you write down the measurement, then they've traveled all the way around that circle and they're back where they started. You look up and you say, oh, they haven't moved an inch. And you record 0 degrees again. You look down, look up, 0 degrees. Now, is that an accurate measurement?
No.
That is not an accurate measurement because you made the assumption that they are moving less than half your sample rate per second. And that's a fatal assumption. And this is something we call aliasing. So that is aliasing a 1 hertz rotation or frequency into 0.
And if you want to ever look at an example of 2D aliasing, if you've ever played a video game that was made maybe in the 90s where there's a checkerboard pattern and the checkerboard looks wonky, or even what's called a Fourier pattern where you take two grids and put them in front of one another, you'll notice that there's like a weird sort of third pattern that crops up, and that's aliasing right there.
Yeah, so we see that there's this third pattern, and it's a low frequency sinusoid. And so for an example of that, let's say instead of 1/3 rotation a second, they did 2/3. So you look, they're at their starting point, you record, you open your eyes, 1 second later, they're 2/3 through that circle. And you record that position. And you keep doing this. Now they go another 2/3, so now they're at 1/3 of the of the entire circle. You keep recording this and you look back at your data. If you look at that, it looks like your foot, the person's foot started in one place and went backwards by 1/3 of the circle. It looks like instead of this person going forward at 2/3 rotations a second, they're going backwards at 1/3 rotation, and that is aliasing. Now that can be very fatal to your measurement, because now you're saying, you know, something's moving forward and you're assuming that it's moving backwards.
I want to say this real quick. I know that we are a bit limited on time. I want to just offer a proposal. What if we were to do frequency part 2 someday? Then we could do all the fun stuff that you'd like to talk about.
We could do that. We could do it with information theory, bandwidth. We could do a communication systems engineering episode if you like.
I am so down for that. Maybe even an episode that's catered to those who are perhaps considering that degree path, or you know, just anyone in particular who wants to know more about that topic.
Yeah. Well, thank you guys so much for having me. I love talking about this stuff.
Absolutely. You've been a very, very well-informed guest.
Yes. Let's do this again.
Adios, amigos.
Ready to level up your career? Text DISH to 44043 now to dive into a world of exciting technician opportunities at DISH. From cutting-edge technology to a supportive work environment, DISH offers the perfect platform for your success. Connect with us today to discover how you can be part of a dynamic team driving innovation. Connect today and join the DISH family, where innovation meets opportunity. Text DISH to 44043 to kickstart your journey towards a rewarding career.